It does feel too loud. Okay. Oh, this is great. Let me take care of this one. Got it. Thanks. Okay, cool. So, hey, everybody. I feel it's getting fewer and fewer people every time I'm here. So, did Gary announce that it's me today and everybody just like not gonna get here? Cool. Anyways, so today we're gonna talk about planning. I know that Gary had like some final slides that he wanted to talk about, but unfortunately he cannot make it today. So I'm basically jumping in directly with the planning lecture. And we will talk about planning and a little bit of optimal control, really. But today will be a fairly relaxed lecture compared to, like in terms of mathematics and so on. So I try to do mostly visual stuff today. So so far, we actually have assumed that we can interact with the environment, right? So if we have our MVP setting, but interaction basically means that we perform some kind of action, right? And then we get the next state back out of it, right? So our little robot here, like acts or chooses some sequence of actions, maybe even, and like that just gets fed into the environment, and then we basically get a next state out of the environment. And this is what we understood as interacting with it, right? So, but that is actually as far as our access to this environment goes, right? This environment often we also call the model or the system dynamics, right? So those are just like alternative terms for that. And but we're basically limited to that so far, right? So we just looked at how we can improve the policy of the agent given this kind of black box environment, right? And that is usually what we would refer to as model-free reinforcement learning, right? Model-free meaning that we don't actually take advantage of the environment or the model. So don't confuse this with the type of model that we would use, for instance, for the policy or something like this. This is just the naming that people usually, or the people back in the day gave this whole thing, right? So the question now becomes, what if we actually have access to the dynamics, right? Does this make things easier for us? And the answer to that is more often than not, yes. Things become easier, right? So there's two cases that we can consider here. So the first one would be that we actually know the dynamics, right? So when is that the case? That is the case, for instance, when like in games, right? Where we actually know, like if I make a certain move, right? I know how the board changes, right? For instance, in chess, but also in Go, but even like in computer games like Atari and so on, right? So if I press the up key, I know that the figure will jump, right? If I press the right key, the figure will move. So I kind of have an understanding, or I even can, like these days, right, with the large language models and so on, I could even just take all of the source code and just feed it into like a model, right? And that model basically now like a neural network or whatever, and that would now represent the world model for me, right? So there is scenarios where we do know the dynamics. And like another point would be, for instance, if the dynamics are so simple that we can actually like just model them based on physical understanding, right? Or physics understanding. So in a car, if I steer left, will go left. If I press the gas pedal, it will accelerate with a certain amount by a certain amount and so on, right? And then again, there's other scenarios where we created the environment ourselves, right, in simulation and these kind of things. So here, if we know the dynamics, right, we basically open up this black box and it becomes a complete white box, right? So then there's this other branch where we say, okay, we might not know the dynamics exactly, like the ground truth dynamics, but what we can do is we can try to learn them, right? So instead of like really opening up this environment, we observe state transitions or other kind of information. We might have prior knowledge that we can take into account, like all kind of things. And that basically allows us to create our own model or like our own version of the system dynamics, right? So this is what we assume to be true, right? And then, so like for instance, if you think about a robotics platform, you might think like, oh, we know the dynamics, right? Like with a robot platform, but it is in the real world, very often there's like tiny nuances that we don't actually know that will affect the actual performance, right? So that might be, for instance, like the current temperature of the robot would affect the gears right? So there's like some, like very often there's like some, I'm not sure what the term in English is, like fat or oil or grease. There's grease, right? And with the change in temperature, the state of this grease actually gets affected, which affects your friction coefficients and so on, right? So there's something like we think we know exactly, but there's components that might actually change that we're not aware of, right? So what we can do is like system identification, where we try to run these things and try to estimate what the friction coefficients with respect to temperature or with respect to time would be, right? And or simply in a more abstract setting, like let's say in a game where we don't have the source code or we're not sure about the rules, right? We just explore and we make up our own model. Like very similar to what happens to you if you play, like I assume you play like, I don't know, like some of those rogue games. What are they called? Like, I'm too old now. Like something with Dark Souls, something like this, right? Like where you try to learn the patterns of the end game boss or whatever, right? Like, yeah, I'm showing my age here. I'm gonna skip this. Can we cut this out of the recording? Like, okay, no, anyway, so you basically make up in your own mind like a model of what the opponent behaves like, right? And then you act accordingly. So this would be like the second part. So today we're gonna look at the first one, which we usually refer to as planning. So for you, right? Model being black box means model free, right? Or environment being black box, model free. Model being exactly or completely known, planning, and model being learned is model-based RL, right? So if we actually learn a model, we call this model-based RL, and this will be something that we'll be talking about tomorrow. So like I said, today we're going to focus on planning a little bit, right? So what we do is we focus on offline versus online planning here, or we distinguish between rather, right? So in offline planning, the name at first glance might be a bit confusing, but I hope that like with this little illustration, it makes more sense. Can you actually see it? Oh yeah, cool. So the idea is that we take the entirety of our world into account, of our world model into account, right? So we create a global plan that allows us to choose our actions no matter where we actually are, right? And we do this offline. So we do this before we even take our first step, right? So if we actually have like if you consider like the entirety of our state space, right? And we parse through it and like we create a model, like if you would want to do it manually, you would have like a ton of if else cases in there, right? So that basically allows me to avoid replanning because I already considered all possible states, right? But as you can imagine, that is quite expensive, right? So it will take a lot of time to compute this depending on like our world model size and so on, or state space. In contrast to that, it's online planning, right? So the idea is basically now instead of, let's use this thing here. So instead of like taking the whole world into account, right? We just like look at local state spaces, right? So where are we right now, for instance? So where are we right now? And we try to learn the optimal policy or like the optimal action for this one, or we plan rather the optimal action for this one. And then once we consider, okay, where will lead us, then we basically learn a new plan for that, which is significantly faster, right? So we can do this much, much faster because we only take into consideration like few state or like a small subset of the state space, but we need to do this more often, right? So we need to do what's called replanning. So like after certain time steps or a certain amount of time steps, right, we basically replan given our current current state. Does it make sense? So this is much cheaper, right? But it requires the replanning. And since we do this basically while we execute or while we interact with the world, we consider this like, we name this online planning. So online planning algorithms, we actually already have seen, at least that's my understanding. So we talked about dynamic programming lecture 3, I believe, right? And so basically value functions would represent this like global understanding. So if we actually are able to compute the true value function, that will be correspond to a global plan, right? Because it tells me like which state is the optimal state to be in, right? And as you already know from back then, that works well only if my problem is small enough, right? So as I already mentioned, often it's much easier to compute this function locally, right? And this is called online planning, or sometimes you will also encounter the term MPC or model predictive control, which is just a synonym here for this one. So as I said, we have to do replanning then. What we can do actually in this case is we can do warm starts, which means that we initialize our current plan with our previous solution, right? I think that should also be nothing new here, right? And this works well in discrete environments, right? So we will look at one particular method here, Monte Carlo tree search. And that one actually, I'm already spoiling it a little bit here. That one was actually able to beat the world champions in Go, right? So, however, for discrete environments, it becomes problematic. And there's a different approach, like a linearization approach, called LQR or LQG, which is like a short for linear quadratic control or linear quadratic regulators. Linear quadratic Gaussian control. We'll briefly talk about this, right? So just like at the very end, like a little bit. So we have online and offline planning, but our dynamics now can also be separated into deterministic and stochastic dynamics, right? So in deterministic dynamics, like as the name suggests, like the same action at the same state will always result in the same next state, right? Nothing special here, very simple. So if I'm like at the red state and I take the blue action, I will always end up at the purple next state, right? In stochastic dynamics, on the other hand, right, there is a variety of possible next states. So there might be effects in our system dynamics that are not fully controlled by the actions. So think about like a table tennis game or something like this, right, where there might be wind, like or other perturbations, or in a collaborative game, right, there might be the policy of my opponent that might not be deterministic, right, so not be like the optimal one, but just like stochastic, some randomness in it. So we either say that deterministic dynamics are a function of state and action, right? Or they model a distribution over possible next states given the state and action, right? So you should also be familiar with those concepts. So if we actually now do consider deterministic dynamics, right, then we can very easily solve this with open loop control. So, or like an open loop planning rather. So the idea here is now that if we already know like how my state will change in the future exactly based on the actions that I take, I can not only choose my current action, right? But I can also choose the next action after that already because I know what the state will be, right? So is that clear? That should be fairly simple to everybody, right? So if not, please like help me help you. Just let me know what I need to clarify, right? So yeah, but basically we can produce an entire sequence of actions up until our finite horizon, right? So we're considering finite horizon cases here. So we don't plan until infinity, we plan until some capital T, right? And we can basically predetermine all of these actions just from my current state. However, if we move to stochastic dynamics, right, there might be some problems because why? Why do open loop plans don't behave optimal in this scenario, or not necessarily optimal in this scenario? Should be fairly evident. If you have a really simple idea, that's most likely correct. Your actions are not the ones that are stochastic here. It's the environment, right? So like if there's a cliff, right, and you observe this cliff, right, and you choose your action, like your action will not, hopefully not lead you off the cliff, right? So, but you're thinking in the right direction. Yes, exactly. So what does that mean? Can you extend the cliff example? Fair. So yeah, let's take the rock. So let's say like if I walk along the cliff and there's like gravel or something like this along the road, right? So and some rocks are more stable than the other ones, and I step on a rock. So my action was deterministic. I did like exactly do what I intended to do, but the environment became a bit more stochastic because the rock that I assumed to be stable wasn't. So I just slip and fall off the cliff. So yeah, there we go. So exactly. So we need to react to unforeseen events, or to basically we need to incorporate the stochasticity of the environment in our actions. So yeah, so basically summarized here that problem in open loop control, or open loop code rule is great if we have deterministic scenarios, right? And we can know exactly what will happen based on state actions. Yeah, we basically plan a sequence of actions. Whereas in like a closed loop, we plan a policy. So instead of just giving like a sequence of actions, we actually plan which action we will take if a particular event occurs, right? Or a particular next state occurs. So if we do this with closed loop, right? So there's like two approaches that we already, or two possible paths that we can go along here, right? So if we already know like a lot about like modeling policies and so on with neural networks, so we could do that, right? But the problem is if we actually would train like a big policy for all of it, that will like for all of the state space, this will take a lot of time, right? And we want to do this online, so we want to be fast. So I don't want to stand like wait like 5 days before taking the next step, right? So luckily, instead of that, we can very often model this whole thing as a linear controller, which can be, which we will see later, later is an approximation of our environment, right? A linearization actually, but it can be very quickly computed. So I can basically have like a relatively stable behavior for every time step because I basically just go along, like, or basically take small time steps. So small changes in the environment hopefully will only occur. Yes. So I do believe that you did not have the stochastic search lecture yet. Am I correct? Have you heard about stochastic search yet? No? Okay, you will. And in the stochastic search lecture, we will talk more about like these approaches for open loop planning, right? So I think like last year, the order of the lectures was slightly different. That's why I wasn't sure if we what we stuck to today. So yeah, but we will revisit this slide sometime later down the lecture. So for now, we're gonna do something which I like to do. We did it last time when I gave the lecture already. We're gonna do 5 and 5, so this will be very fast. So we can actually do this 3 in 3 minutes. But the idea is that like you cluster in little groups, and you think about what you've just heard. So like this will like was just a bunch of definitions. So I think that we will be fairly quick. But yeah, please take like 3 minutes, take out like a piece of paper as a group, right? And write just down 3 questions. And then you exchange it after 3 minutes with another group. And then you try to answer those questions, right? Try to make it ideally like split those 3 questions up into like difficulty. So like a very easy one, right? So if you just woke up, you should be able to answer this one, and like an average one that you should be able to answer when you paid attention. And then like another one where you're actually not sure about your answer yourself, right? So just let's do this very quickly, 3 minutes, and then switch for another 3 minutes. Cool. Hello, hello, hello. Okay, cool. So how was that? Did you come up with some interesting questions? So let's just go around. Like, did somebody have like an interesting question? No, they're all super boring. So what were? Yeah. You want to show whether if you have either the black box model where you don't have any information about the environment at all, and you just get our states back from the action of it, or if we know all the information about the model, so the environment, um, is the one where we have all the information about the environment with the model base. So like it really depends what you choose to do. Like this model free, model based. So I don't know if this was audible in the recording, but so the question was like the exact. I rephrase it like the exact threshold of where model based, model free changes, right? So and it's really like less of the setting that is given to you, but what method you choose to apply. Like even if it's a scenario where like you know the entire model and all of it, right? If you choose to ignore that information and treat it as a black box, right, then you're model free. If you say like, you know what, like I want to use all the information exactly, right, like as it is in there, right, and basically build my value functions on top of that, right, like with dynamic programming or whatever, then that would pretty much go into direction of planning. If you choose to say, okay, I have like even if you have all the information, right, but you choose to plan like your own model because you don't trust that information for whatever reason, or it might be too complex and so on, and you basically have a proxy for that you learned, right, a model, then you're model based. So it's really like up to what you decide what to do. But that will be the definition. Does that help? Okay, cool. Any other questions? I think you can, I don't think like you have to be, I don't think it's a one-to-one mapping. So you can do, um, where do we have the definition, right? So if you look at definition here, right, offline planning basically just means that you consider the entire thing, right? And so you can actually, the question is if you should or not, right? But you could do, for instance, like closed loop on that one too. Yes. Yeah, you could do closed loop on that one too. Like it wouldn't make much sense, honestly, right? Because like well, it depends if it's deterministic or stochastic. No, mhm. No, closed loop basically means that like you're trying to like you model a policy, right? Like you don't model a sequence of actions, right? Yeah, but like so here at this point, it really depends if it's like stochastic or not, right? So you can, yeah. So what were you saying? Yeah, yeah, sure. Yeah. That's why I said it depends if it makes sense. Like, if it makes sense or not is a different question, but you could serve it, right? So yeah, but does that roughly answer your question? Okay. Anything else? Mm, we actually have an expert on that here. So, like, would you say that open loop planning is the same as episode-based RL? Mm. So it's basically not a one-to-one mapping, right? So, yeah. But those are good questions. See? Nice. Yes. Because that's a good, well, it's a good question. So the question is, because it's so good, I will repeat it. Like in chess, right? Like you don't have control over your opponent, right? But in chess, you still have a finite amount of actions that your opponent can take. So you can basically model all of them. So your branching factor, well, you don't know what the branching factor it is, right? But like basically what happens is that like you consider all possible actions, right, of your opponent and model them, right? Or take them into account, let's say. Hmm. Cool. So then let's move on. So I already mentioned that today we're going to talk about MCTS, right? By the way, we were debating in the break, am I too fast? Should I go slower or am I too slow and should go faster? Or am I okay for speed wise? So who thinks I should go slower? Nice. Who thinks I should go faster? Nice. Who thinks I should just leave? Oh, I saw that. Okay, cool. So now we're going to basically talk about closed loop planning in discrete domains, right? So in particular, will talk about one method. Well, actually, we will mention the second one, but like we will talk about mostly about Monte Carlo tree search here. So the idea is that if we have discrete domains, right, that we can represent discrete domain space, discrete states, discrete actions, right? We can represent our like policy or like our world, let's say, as a tree, right? So where basically the nodes would correspond to the states, right? And the actions would correspond to the edges, right? So here, for instance, in this kind of tree, right? Like, so this would represent two different actors, right? The white and the gray actor, right? And in this notation here, we will revisit this. That's why I explain it here. Now we basically have like before the dash, it's the number of wins that we had in this particular game. And after dash is just overall visitations of that state. So how often did I actually end up in this state, right? And how often did I win after being in that state, right? So, and I hope this is clear how we can actually transfer pretty much every deterministic or every discrete domain into a tree like that. So I don't know how many of you are familiar with Minimax? Show of hands. Oh, not that many actually. Okay. So Minimax is a search algorithm, let's say, if you want, right, for trees, right, and in particular for games it's used, right. So the idea, the name suggests it already. Minimax basically says that I will, if I consider that it's a turn-based game, right. So like I will do something, then my opponent will do something, then I will do something again, then the opponent, and so on, right. I always choose for myself the action that maximizes my reward or my chances of winning, right? But then if I need to look ahead, right? So what will I assume that my opponent will choose? What do you think? Exactly. So the action that minimizes my return, right? So basically that's where it's the min and the max come in, right? So basically I choose the action that maximizes my return, whereas I assume that my opponent will choose the one that minimizes it. So if I look ahead and basically plan for what my final action should be, right? Or what my action right now should be, I look down all possibilities down the line, right? And choose and always assume that my opponent plays optimal. That's, by the way, also one of the big downsides of Minimax, because if opponents start to play suboptimal, that can actually go wrong. So you might actually behave worse if your opponent plays badly. Who knows examples where this is happening? What games do you get? Like, just out of curiosity, like I want to know. So what games do you know where at least not like in finite time, you will perform worse if you play optimal and assume that your opponent is optimal, but your opponent is suboptimal. It seems counterintuitive, but there's a lot of examples, a lot of games there. Any idea? Does any one of you play poker? I'm too old. Like, so in poker, basically, like if you there's like you always assume that the opponent is basically smart, right? So basically they would lay down a hand if they would know that the hand is really bad, right? But then they don't, and then they luck out, right? And then you just get furious because you played optimal and they just bad, but with a lot of luck, right? So this would be one example. But actually the same is true also for like board games like chess and so on. So okay. So can we use Minimax here in this case, right? So like, well, the answer, or generally in our planning scenario, well, the answer is it really depends on the domain size, right? So there's something called the branching factor in trees, which means like the average number of children per node, right? And that kind of like gives you, in our case, it would be the actions, right? And it kind of gives you already an idea of when this whole thing will break down, right? So so if the branching factor is too large, so which basically determines the breadth of your tree, right? And you have too many states, which basically determines the depth of your tree, right? If those two are large, then Minimax will just not work anymore because there's too many states and too many possibilities to visit. Does it make sense? So I cannot cover like all of the search space in a feasible amount of time. Okay. However, who would have thought, but chess apparently is not that complicated, right? So because back in 97 already, Deep Blue, and I know I will get letters for that statement, right? The chess isn't complicated, but whatever. So in 97 already, Deep Blue actually won against Kasparov with a simple, well, simple compared to these days, min-max strategy, right? So even though you have like a ton of options, right? If you actually have enough compute and you can build up this tree, Minimax here would still work. But if we actually look at other games, right, like for instance Go, right, or just like any current computer games, then like just by the sheer amount of options that we have, so the branching factor, right, just because that is so big, Minimax is not a feasible option anymore, right? So what can we do instead, right? So if we like assume like our discrete state space, right? So it's discrete, but still huge, giant, right? And we have board games like Go, for instance, or computer games like Atari, where this is the case, right? And we like, so we see that like Minimax is not an option anymore, but also dynamic programming is not like, will not work here anymore. So like, even in such simple games as Atari, and if you now look at StarCraft or whatever, then like you wouldn't do anything in this direction. So question is, can we still use some kind of tree search, right? Or like tree-based algorithms, like if the transitions are stochastic and so on, right? Yes, the answer is MCTS, like or Monte Carlo tree search, named after the famous gambling city in Monaco. So, and the MCTS, the nice thing is that it actually is very similar to Minimax, but it's like a smarter exploration strategy, right? So we're gonna split it up, right? And it still tries to follow an optimal path, right? Also assuming or taking into account the behavior of your opponent, if there is one, or the environment in that case, or in another case, right? But we can still use this tree representation and explore it like feasibly, right? So actually it's even an anytime algorithm, and we will talk about this, or I'll just briefly mention that in a second. So Monte Carlo tree search, how does this work? So here, just to explain basically what we see is if you consider that this would be all of the tree, right? So like, and so so the entirety of this well, not really triangle, like pentagon kind of thing, would be our search, like our overall possible state space, right? State and action, I should say. And the search tree is the one that we know already. So we actually already made our mind for this part of the tree, right? So we actually already have some data that we base our nodes or the value of our nodes and our actions on. They might not be 100% accurate. They're not good necessarily, right? They're not exhausted for sure. But based on everything we've seen, we already have like a certain amount that we feel comfortable in walking along, right? And then there's this part here, which we just don't want to say anything about yet, right? So then basically MCTS is an anytime algorithm. Who knows what that is? Just real quick, computer science students. For the win. Anytime algorithms are algorithms that produce a result at any time. So if you leave them run longer, right, they might give you a better result, right? But if you just need one right now, they will give you the best thing that they came up with right now, right? So which is actually very nice for settings like also chess and so on, where you have the clock. Yes, and it basically explores the trees asymmetrically. So it's not like a balanced tree or something where it tries to always have like the same number of leaf nodes for every child node and so on, but it doesn't really care about the structure of the tree at all, right? So it really just tries to expand it. And the way that it works is basically that the most promising subtrees are visited more frequently. So if we have now the search tree over here, right? Then well, the image doesn't really give it, but there's several, like imagine that there's like several nodes in there that we just discussed, right? And for every node, as before, we basically have some indication how good this node is. So this could be the win, right? The wins that we did in a discrete setting where we basically just win and lose, but it could also be something like the Q values, right? Yeah, and then we have two phases that we go through here. We have the tree phase where we decide which path we go along the search tree, right? And we have the exploration phase or rollout phase where we basically go along the explore trees and simulate, simulate is the term that we use here. We basically just choose a different type of policy that will lead us through this exploration tree to see how well we can perform in there, right? So in the tree policy, we basically start at our root node, or like the root node would be whatever our state is right now, right? Or like if we do this like offline, so before we even start playing, we just use the empty board, for instance, in chess or in Go. And then we have a particular way of going through this path. And then when we're at the leaf node, we add now a new path or a new node to it, right? So how do we actually traverse along this red line, or how did we choose this red line? We actually just use the UCB algorithm, right? And I think you heard about UCB already in the lecture. Is that true? UCB, right? Upper confidence bounds. Cool. So basically what we have is our, like, oh, you cannot see this. So what we have is our estimate how good the state action combination is right now, right? And then we have an exploration term. And the exploration term basically makes sure that we don't always go down the same path, right? So the way that you can like intuitively understand this equation here is like that the more often you ignored a particular node, so like the more often you didn't choose that node, the higher the chances of randomly visiting this node the next time around will be, right? Is this clear? So, and this makes sure that I don't basically get stuck in a local optima, that I'm actually like branching out, right? No pun intended. Yeah. So, and then basically once we are there, we add our new node. And then from that new node, we have our rollout policy, or like that could be, for instance, or fairly often it just uses a random policy, but it doesn't have to, right? If I have like something smarter that I can follow, you should do this. But the general idea here is that we, from that moment on, we will see more states, right? We will, like all of those are actually states that we will visit, right? But we don't take them, or we don't incorporate them into our search tree. Those are just like from that state on, or from that position on, right? Those are possible paths that lead us to a final result, right? And this final result will be, for instance, winning or losing, or will be some return that we will get, right? But we literally just, or we literally just care about the result. So, and then we take this one into account over here. So these nodes along the path, they're just there because they're required to get to our return, but we don't incorporate them yet into our search tree, right? And we can do this a lot. So here's just like one path, but I can have like many, many more simulations, right? And that gives me an approximation of how good it is to be in this state. Because like if all of those simulations, no matter how many I have, they fail, right? Like I lose, then this might not be a very desirable state to be in, right? Does it make sense? And it doesn't even matter like if for whatever reason, right? So because we follow a random policy, for whatever reason, this one would still be actually a good state because there's like some branch which will lead me to a good goal, right? But I always choose to, or I more often than not choose to go over here, and then I end up with like something very bad that still affects this new leaf node, right? Okay. So it's a little example over here. So we start with the so we basically go through 4 phases or 4 different steps, let's say in here. We start with our root node, right? So the count, like again, the notation here is visitation count and number of wins. Pay attention that it changes because here basically for the, so the first digit is with respect to the color that we're in, right? So the white player won 11 out of 21 times in this node, right? Over here, the gray player won 7 out of 10 times, which means that the white player lost 3 out of 10, right? Does it make sense? No, if the gray player won 7 out of 10. Oh, sorry. Yes, exactly. Sorry, yes. And that's basically if you go over the first digits over here, right? Because overall there should be 10 losses for the white player, so 10 wins for the gray one. So for all actions that we can take, we sum up the first one and it would be 10, right? So does it make sense, this notation? Yeah, perfect. So, and we basically follow this path, right, that is weighted by the UCB that tells us basically, okay, how often did we perform well in here and how often do we visit that node already, right? And that leads us to 3. So we then do an expansion, right, where we say, okay, we choose one action and get our new leaf node. We do the simulation, which is the random policy, which just basically, oh, actually, I have that in here, right? So we do the expansion, right, which just brings us to the new leaf node, or the new node C rather. And then we do the simulation where we just finish the game from that moment on, right? Like with a random policy or like a rollout policy rather than a random policy. It can be random, doesn't have to be, right? So, and then we basically backpropagate that information. So what does this mean to backpropagate the information? Well, in this case, we lost as a white player, right? Because we're looking for the white node or root node. So we lost. So we were here once and didn't win, which means that we increase all the visitation counts, right? Along the path, and then basically alternate between increasing the first number and not, right? In the same way we would update basically our queue function. So that's fairly simple, right? Any questions so far? So the actual selection phase, right? It's the one that you lost most, but you also have been there a lot, right? So right. So basically, like the more frequent you are in there, so you yeah. So basically, like the visitation usually plays a bigger role in that, right? So the more often you've been there, the more often you assume, like because you only end up, you start choosing it once you behave well in there, right? Overall, yeah, sure. But like actually, but actually, the visitation count does play a bigger role than the actual value. Yeah. What do you mean with alternate? Oh, this like that's just the visualization here. I mean, like the reason here is basically that you can always, because you still follow like kind of this min-max thing, right? So you can easier see that you always go along the maximum numbers, right? Okay, so yeah, we basically propagate everything back. So propagate, don't confuse this with back propagation, right? Like in this case, it's really just like updating the values. So now the question, looking at AlphaGo, I already gave it away in the introduction that we actually can, or MCTS was successfully used to play Go against humans, right? So why is it even harder in the first place? Well, the branching factor is huge, right? So it's like a lot of options that I can take at any point, right? And brute force is just not feasible, right? So if we basically just want to cover the entire search tree, there isn't enough space in the world for that one. And it's actually for a long time was considered like impossible to cover that, right? But AlphaGo kind of managed. So the way that they went about it is that they trained a CNN. I will not introduce CNNs here now, but basically the CNNs were used as value networks, right? Or value policy functions. And they basically tell you like, okay, from the current state, right? So what is the value of being in that state at the very end, like after n convolutions? And the same for the policy, how important is it to basically take particular actions, or how good is it to take particular actions? And they trained AlphaGo in several stages, right? So we started, or like they started with just human demonstrations. So they had like a lot of data of people playing against each other, right? And they took that into account, like a lot of experts mostly, right? So like really well, well-known people in that scene. And they tried, or they first learned a supervised or a policy using supervised learning, right? So just from observing those games, right? What did people most often do in a particular state, right? So that should make a lot of sense, right? So there's nothing, no magic involved there. Afterwards, they said, okay, so now that we have policies that behave as well as humans, roughly, right? Like as well as the experts, can we improve by just letting them play against each other? So we have like a self-play phase where we use reinforcement learning in order to update our policy even further or improve it even further, right? And we continue that afterwards. So once we have like our better policies, we now use the reinforcement learning policies to play against each other. And out of that, basically, with regression, we can then extract our value network. So we're going to look at those different states now, stages now at this point, right? So we basically have our 12-layer convolutional neural network as our policy network here. We had 30 million positions from human expert games. And we basically maximize the likelihood by stochastic gradient descent, right? So nothing fancy, nothing new here. So the interesting thing, or like the impressive thing here really is that it took 4 weeks on 50 GPUs back in the day. So this was 2015, I believe. And it achieved like an overall accuracy of 57%, right? So that was better than anything that was there before. And this was just achieved with supervised learning. So there wasn't any like additional exploration happening. So with that, basically they then updated the policy network. Again, 12-layer convolution network, but the training idea was now that we use reinforcement learning with basically self-play. So meaning that we play against ourselves all the time, right? Or like the network against itself. And we have here the most basic reinforcement learning algorithm applied, really just reinforce, where our return is basically 1 if we win and 0 if we lose, right? And we basically add that just to our policy gradient, and that's pretty much it. Or we don't add, we multiply it, but yeah. And then we do gradient updates. Okay. So this one trained on 1 week of 50 GPUs, and it actually performed significantly better than before, right? So now we actually have an 80% success range against the already better behaving supervised learning policy, right? And then since we extended this even more, we now basically, or they now like introduced or computed the value network, right? Again, just the computation of the value function as we know it, as we've seen it like a lot using the MSE here. Nothing special really. And but I should maybe mention, the nice thing is because of the simplicity of all of those parameter updates, right? Like starting from the policy network or from the supervised learning over the reinforce, over now learning the value function. They're very simple, right? But that also means that we have fewer assumptions, which means we introduce less bias in here, right? We don't have like domain approximation. So they're simple, but closer to the actual ground truth. Make sense? Yes, and that needed another week on 50 GPUs on the Google Cloud, right? And it's the first, or at that point, it was the first ever way to evaluate like the value of a function, or of a state, the value of the state in a game of Go, right? So before that, as I said, simply because of the state space, the size, and so on, people didn't think that was actually possible. Okay, so we now basically can use this or like have this MCTS thing or MCTS structure, right? Where we use deep learning in order to optimize it, right? So how did this behave in the past? So if we actually look at the AlphaGo 2015, right? It was able to win against the European champion back then, right? So in actually 5-0 match. However, that was, like I said, the European champion, not like the world champion. However, just a year later, with like more self-play and so on, right? So it actually managed to win against the person that was back then considered the best player in the world in Go. Well, actually with a clear margin. Yeah. So that was quite impressive and depressive for the players, right? Because like now we also, or AI also solved Go, basically. So to wrap up MCTS, it's a very successful planning tool, right? So it actually has been extended a lot based on, for other domains, right? So for instance, you might have heard recently about AlphaFold, right? So actually it's not that recent anymore. It's like also like 2-3 years ago, right? When was AlphaFold? 2 years, yeah. So basically where we can use it for complete different domains like protein folding, right? Which is again something which was considered very hard to do and like, well, specifically for humans, but AlphaFold also in a very similar way as AlphaGo managed to do this. So by the way, the new version of Alpha or the current versions of AlphaGo don't use the supervised learning part anymore. They actually start completely, or they start completely from scratch. Yes. And with that, I think we're done with MCTS. I would ask you again to do this 5 and 5. I think this time there's more things to ask about. So yeah, again, get out your pen and paper. Or before we do that, is there any questions you would like to ask? So that's an interesting question. Who has an answer to that? So in this particular scenario, right? Like there is no such thing as the same identical state, right? Because you like in Go, you always add pieces, right? But yes, you would basically go back to the previous state, or you would actually well, you don't actually um, you don't need to break the tree structure, right? Because you've been there already. So you would recognize that this is a visited state already, right? So like, and if you have the scenario, then there's also no winning or losing, right? Because you would keep running in a loop. So we just not choose it. Make sense? Yeah. Okay. Cool. Awesome. Okay. So who had some interesting questions, or who thinks they encountered an interesting question? All of them were boring. So what was the easiest one? Let's start there. Sure. You said for the new workers, they don't do this supervised learning step with the expert positions before, but they do all from scratch. Yeah. This I assume all like self-play. Like, yeah. Yeah. Like behind that, because I think it's gonna be more expensive. So yes or no. So the problem is that even if you start from a expert policy, right, you're basically already in that limit, right? So you're basically in that local optima already. So you can, through a lot of self-rate, try to break out, right? But you limit yourself already. Whereas if you start completely from scratch, you might find, let's say, for instance, let's say like similar, I'm not a Go player. I'm not a chess player either. But if you, I know that there's like certain opening moves, right? Both in chess and in Go. If let's say the first 10 or even 50 steps of a chess or a Go game are always like very like, let's say predetermined through experience, right? So people know like if you play this, I play that, and so on, right? And then this will always be the beginning, right? Because like all the observations are that, right? Like the A to B answering. However, if you do a random thing, you might actually end up discovering something, or like if you start differently, you might discover something that currently is not considered a good move, right? Because if you do this move, there's like 50 answer moves, right? And there's like whatever. And nobody had the idea that like, oh, if you do this move, you lose in 4, right? But then actually it turns out if after 3 you do that one particular move, you win, right? But nobody ever went that far, right? And this is actually what happened for other games already. So I'm not sure for Go. I think there's a similar story for Go, but there's definitely one for backgammon, where like even before that whole thing, TD Gammon, like a temporal difference approach, did introduce new moves to the game of backgammon, which are now basically taught as expert moves, which before that nobody considered. So yeah, that would be like a possible answer to that. Hmm? Anything else? Nothing? You just had like 15 minutes of nothing. So what did you talk about? Like up there, what was a cool or not so cool question? Yeah. Yeah. So alphabet. Yeah. So alpha beta pruning makes a lot of sense, like in the context of min-max, right? Or minimax, because we do this full exploration part of it, right? So whereas here, where we like focus on the smart exploration, or what we consider smart exploration with the UCB, yeah, I'll agree with you that yeah, that there is no real need for it, and it might actually be harmful even if done like just naively. Okay. Cool. So with that, we're done with MCTS, right? And I promised you that we will look at closed loop planning for continuous domains and optimal control. So we will be very like brief here. This is the math heaviest part of the lecture, right? But like I will tell you exactly what will be relevant for the exam and not, right? And where you can find more information for the interested reader, right? So let's go through this. So in this finite horizon setting, like as we before, we don't want to look until all the way until infinity, but just like until a finite domain, right? Or final time horizon. We have our like expected reward as usual. So there's nothing special here. The last in the finite horizon scenario, the last reward does not depend on an action anymore because we are at the last state, right? So that's why there's this RST already. And so the question becomes now, if we now have continuous states and actions in this setting, is there a solution, right? So can we actually like still do planning here? And the unfortunate answer is like, in general, no, right? So there's no closed form solution in general, or nothing that makes like efficient or is efficient enough to make sense. However, there are certain assumptions that we can take, right? That will make an analytic solution possible. Right? So, and in particular, those assumptions are basically the LQG assumptions or LQR assumptions. Um, so LQG, did I just say RQG? No, LQG basically stands for linear, quadratic, Gaussian systems, right? And the idea is basically that, again, we have our normal state space. Since this comes from control, just so you know, if you ever see this in literature and so on, in control theory, you usually use X for the states and U for the actions, right? Instead of S and A, as we do in this lecture mostly. And it can be time dependent, but it doesn't have to. However, the linear part of LQG is basically that our dynamics are linear, right? And we add Gaussian noise. Then, so which is basically what's happening here. So it's like clear to everybody how the dynamics like are linear, right? Okay, so this is just a linear equation, linear dynamics, right? And we add Gaussian noise to it, right? So which usually it's just like a little bit of white noise. Our reward function we assume to be quadratic. So we basically have this, it's vectorized here, but this is basically the quadratic term, right? For the states, right? And for the actions. So consider, I'm pretty sure you talked about action punishment already, right? So that you want to choose like smart actions. So if you can, like if you consider the whole regularization thing, so the parameters that you want to choose, if you have infinite solutions, are the like usually like the smallest ones, right? And the same things for the actions. If you can achieve the same thing with different actions, you kind of want to use like, in this case, small ones for the reason that those are often, for instance, considered torque or acceleration, right? And if you just do this without any punishment term, then you might end up with what is usually referred to as a bang-bang controller, which just means that you go as fast as possible, and then like in the latest possible time, you go as slow as possible, right? And that basically just jumps between the two maxima, and you want to avoid that, right? You don't want to break your robot, so or your car or whatever. So basically, those are those two matrices here that regulate the reward with respect to the actions and respect to the states, right? And then finally, basically, our state density is Gaussian, right? So that's our LQG. That's what LQG stands for. So, so if you don't take anything away from LQG, remember which parts are linear, which parts are quadratic, and what is Gaussian. Okay? So, yeah. Again, this is basically what I already mentioned, like the linear system with Gaussian noise added to it, right? So we basically have our system and control metrics because it's added to the actions, right? To the control signal, let's say, and system metrics because it's added to this, or like, sorry, multiplied to the state, right? So to a system. We have like drift terms, which are basically constant offsets, right? And we have our Gaussian system noise, which is sigma at this point. And the quadrivial function, I already explained it also, I believe. So this were already a lot of equations. Any questions so far? Is this clear here? Do you guys know what the muddiest point is? Have you heard ever about that? No? So the muddiest point is the last point where you still paid attention. Like, so it's the one where you still remember what we're talking about, right? So like, what is the muddiest point here? Should I just proceed? And you want to look at it again later? I'll basically just cost. We basically just assume that we want to minimize the cost. You can always maximize the reward or minimize the cost. And usually in control theory, we think rather about costs than rewards. Okay. So if you take our, like as a little example here, this reward function, this is not very well visible, is it? Damn it. Okay, maybe make a note that for the future we take different colors for this plot, right? So basically there's two different slopes here, right? Like half pipes if you want, in our reward function. So we're trying to be, basically we have two particular points at time step 15, time step 100, where we are very specific about, like we want to be there, and for everything else we don't care, right? Like for the other states, we don't really mind where we are, right? But we have to be at those. And this is basically what the, how we construct our reward, right? So that basically at time step T1, which would be time step 50, and T2 and so on, we basically add a lot of weight. So meaning that the distance between the action, right, and the where we want to be, like our via point, will be punished a lot if it's wrong, right? And if it's very small, then it doesn't affect our control that much anymore, right? And for everything else, we don't really care. So we make very small punishment terms on them. Okay. Cool. Oh yeah, so side note, in this scheme, RT and HD always have to be positive definite. Otherwise, none of this works, right? So actually, do we want to go about this part? No. So this, we don't need the refresher here because we're not going to go too much in depth. So basically what we need to solve now for the LQR system is the expectation over the next values, right? And we then do like an maximization optimization over that to get basically our policy out, right? So we have like these two steps that we try to solve. For the full case, brace yourselves. This is what it would look like for like the full case. So there's a lot of math. You will need to know all of this by heart for the lecture, right? Obviously not. No, so this doesn't really matter, but like that you, like the reason why I kept this slide in here, right, is that you see that there is a closed form solution, and I didn't just tell you. But like what this really means is that like all of those matrices we actually know, right? They're like well defined. They can be computed efficiently in closed form because they're all just matrix multiplications, right? So we can do this extremely fast, right? We can do this very fast for reasonably large domains. So and like I said, forget about this part either. So, and just to show you that it actually works, if we basically have our position, velocity, and acceleration would be our control term. So that's what we actually fed into the system, right? But the via points were in position space, right? We can see that we actually like managed fairly well. So we actually converge always to the desired states at the desired times while having variance everywhere else. But you can see here that we still have like this extremes over here. So, and the way that we would deal with them is basically to adapt the H matrix, right? But this is exactly what we're talking about, that they basically just jump up and down, right? Because they need to break. So I don't know why this is in here. Oh yeah, and we can the same way visualize the value function in this part. So the interesting thing here is that like, yeah, so the more we can play with the control cost, right? So the more accurate or inaccurate, or sorry, not controls, the rewards, the more accurate and inaccurate we will be at our via points, right? So we basically also need to tune that, similar as we would have to tune a reward function for the other reinforcement learning approaches that we've seen. So now the question is, when is this actually useful? So just real quick, how much time do we still have? Okay, so the thing is, you say like, okay, this is great for linear control and everything, right? But if we actually end up in the real world, it's very nonlinear, right? So like this simple case of the swing up, right? We actually see like that this equation doesn't look very linear, right? So what we do now is what you all know from high school calculus still. So by the way, this is what the value function would look like. We do linearization. So we do a Taylor expansion, right? And linearize it to the first order. And then we have like our linear system again. So does it make sense? That makes no sense at all? Okay, which part does not make sense? We have a nonlinear system, right? So do you worry about the equations? Don't worry about the equations. Listen to me. Listen to me, okay? We're gonna do this with -6 minutes left. We're gonna do this quick, okay? So basically, if you have a nonlinear system, right, it will locally still be linear, right? At any point, I can still make a linear approximation, like if you have a curve, you can put a tangent anywhere, right? Make sense? So for that particular point, I can make a linear decision, right? So, and this is where the Taylor expansion comes in. For that particular point where I am, I linearize that system, right? And use my linear control there. The problem with that is, of course, my system is not linear, so I'm pretty much screwed, right? If I'm going to continue, but I can do this so fast that I just redo this after every step, right? And yeah, so this is basically ILQG, right, or ILQR, where the idea is that we basically do this iteratively, right, and we can do this like for every time, so we solve it again through linearization, very simplified. And then we can do really cool stuff, right? Where we can basically, come on, Emo. So where we have like complicated systems still, which can do like even more complicated and cool. Like, why does it not scroll forward? Oh, it does. Where we can do like complicated manipulation and so on, and all of this with just ILQG. Okay, so to wrap up, we can do it for continuous times on actions, but only if we have certain assumptions, which are, what are the L, Q, and G stand for? Anyone? Nobody's allowed to leave before somebody answers. And then Gaussian state distribution and Gaussian noise. Correct. Okay, cool. So with that, we're going to do another 5 and 5. No, I'm kidding. Since we're over time, like, please leave, but feel free to still do this after lecture. And yeah, thank you.